Yeah, so I will introduce him today. It's our pleasure to have to host Sean Ressler from the BHI Colloquium. Sean is currently at the UC Santa Barbara, and he very recently graduated at the UC Berkeley, where he was an NESSF fellow. His work focuses on making predictive models of higher energy astrophysical phenomena using both semi-analytic calculations and numerical methods. So please, Sean, take it away.
Cool. Thank you. Let me just start sharing. Hopefully you can see that. So thank you, the organizers, for having me here. And of course, I use here in the air quote sense of here. It's much easier coming to Boston when all I have to do is go down the basement and plug in my computer. But here I'm going to be talking about simulations that I've been doing of accretion in the galactic center onto the supermassive black hole known as Sagittarius A star, which I'm sure most of you are very familiar with. Using simulations that particularly take into account the stellar winds of orbiting massive stars. So I've done this is work over the past several years. So this has been with Chris White, Elliot Quadert, and Jim Stone. So just to orient everybody, so Sagittarius A star almost needs no introduction, but the recent Nobel Prize was just awarded to Andrea Ghez and Reinhard Genzel for their decades-long observational campaign monitoring the orbits of stars around the center of the galaxy, which then led to the conclusion that there is this supermassive black hole in the center. So this is just a movie of observed orbits of these stars in the infrared that you can see over decades as they move around. There's clearly something they're orbiting around, and they concluded that there's this supermassive black hole of about 4 million solar masses in the center of the galaxy. And so you can also look at it in the X-rays, and what you see is you see point sources of emission in addition to, so that's just what these ABC things are. And you also see a bunch of diffuse hot gas. So what this is, so most of these point source emission, these point sources are Wolf-Rayet stars, which are massive stars, O-type stars that are in a particular phase of their evolution where they have very strong stellar winds. And these stellar winds provide all this hot gas that shocks with the rest of the hot gas and produces this diffuse X-ray emission. So to give you an idea of how much mass is actually being emitted by each of these things, so one Wolf-Rayet star has about a mass loss rate of about 10 to the minus 5 solar masses per year. There's about 30 of these stars orbiting the galactic center at about on parsec scales. Then the actual accretion rate onto the black hole is somewhere around 10 to the minus 9 to 10 to the minus 7 solar masses per year. So just one of these stars already has orders of magnitude more mass being fed into the domain than the stuff that's actually reaching the black hole. So there's a significant amount of mass supply provided by these stars, and presumably they provide the bulk of the accretion flow. And then of course you have the Event Horizon Telescope, which is going to be, so again, needs no introduction in this, this environment, which will be observing at 230 gigahertz, able to resolve the event horizon, the shadow of the black hole. And I'm not going to ask when or make a statement about when this is going to come, because I'm sure every single person in the collaboration for the past 2 years has been asked every single day, about 10 times per day, when the Sagittarius A star data is going to be released, but I'm sure it's coming and it will be exciting when it does. So how do we study? So those are some of the observational features of the galactic center. So how do we actually model what is being accreted onto the black hole and the emission that it produces? So generally, the most sophisticated tool we have is general relativistic magneto-hydrodynamic simulation, so GRMHD. So all these simulations are, to simplify them, is basically a fixed Kerr metric of a rotating space-time, or rotating black hole, plus ideal MH. What did I just do? Did I just do something? No, there we go. Okay, I can't see my mouse, but I can still click, which is not a good thing. at plus, so it's fixed Kerr spacetime plus ideal MHD. So the equations of ideal MHD plus general relativity, and you have these general relativistic simulations. So then, of course, so those are that's the physics that goes into it. But then you also need some kind of initial conditions and boundary conditions to actually set up the problem. So what do we do? So the simulations generally start, this is not uniform across every computation, but most simulations start from something like this. So this is just a diagram of a torus. So this goes around into and out of the page and wraps around. This is a torus and hydrodynamic equilibrium. So there's the hydrodynamic solution for equilibrium around a rotating black hole. So if you just let it run forever, it would stay in this configuration without magnetic fields. But then you throw in a weak magnetic field, which is what these white lines are. And you see, and what happens is that even for a weak magnetic field, this configuration is unstable to what is called the magnetorotational instability, where the magnetic fields end up transferring angular momentum between fluid elements, and stuff starts to fall inwards towards the black hole. In this configuration, there are several free parameters, and I break it up into what is chosen, what is fit, and what is ignored. So what is chosen, and perhaps the most important choice here, is the field geometry. So whether there's the one loop like I show here, 2 loops, 3 loops, 400 loops, or whatever you want to put, that tends to have the strongest effect on the resulting flow, as well as the entropy or the boundedness or the temperature, or however you want to put it, of the torus itself. So that sort of determines how the propensity the torus has for driving outflows just hydrodynamically based on how bound it is. And then you have what is fit. So GRMHD simulations are scale free if they don't include radiation. So you can just scale the units to whatever fits your needs. And so what generally happens is you do some kind of radiative transfer calculation on the simulation, compare it to observations, and scale the mass of the torus to fit the data points. So you can only do this once, so you can't fit all the data points. So you got to choose one of the data points that you want to fit, and then you scale the mass of the torus accordingly. Finally, there's what's ignored, which is sort of the stuff that I showed before, where all the stuff that's actually producing the mass that creates this torus, large radii, boundary conditions, that kind of thing. So you just assume that the gas from large radii comes in, forms something like a nice torus, and then accretes onto the black hole. And then this is just an idea of what a simulation looks like. This is from Chris White. I don't know if this is from a published paper, but he sent this to me. And if all the GRMHD people know that we have like millions of these just lying around. So the left is the mass density, right is the ratio between the magnetic pressure and the thermal pressure. And so you see how it starts in equilibrium, then becomes unstable to the MRI, starts accreting, there's turbulence, all this kind of stuff. And that's just a quote unquote standard GRMHD simulation. And basically nothing exciting happens after this point. It's fairly constant in time. So then what you do is you take one of these simulations, you run it through ray tracing algorithms, and you can get various, so these are predictions for the 230 gigahertz images, infinite resolution images, not the resolution of EHT, but just for theoretical consideration, what the images look like. I just took these from a variety of different papers to show you how many people have been working on this. And then you can take all these simulations and compare to actual data in order to start eliminating models from what can reasonably fit particular systems. So for instance, in the EHT5 paper in 2019, they had this very large table of all these different GRMHD simulations, fitting them to several different observational probes, and ruled out a number of models using this this technique of just eliminating based on observations with these GRMHD simulations. But one issue with this is that the constraints are not strong enough to eliminate a majority of the models. So you still have, or they eliminate most of the models, but there's still plenty of freedom in the models that are allowed, I should say. So for instance, there's two broad classes of accretion flows that are allowed by these comparisons to observations that are still allowed, but they have much different physics. So one particular thing, they get broken up into two classes based on how much magnetic flux is available near the horizon. So there's this dimensionless number that you can measure. Basically, it's the magnetic pressure at the horizon compared to the ram pressure at the horizon, the ram pressure of the accreting gas. So if this pressure is less than a certain factor, so it happens to be 50 empirically, we find that 50 times this ram pressure, then you get two very different, whether it's less than this or about equal to this, you get two very different states. So first, if it's less, you get sort of what I just showed before, the quote unquote standard GRMHD simulation. You have MRI-driven turbulence and a rough steady state is reached. On the other hand, if you have more magnetic pressure, or you have magnetic pressure that is roughly equal to this value of 50 times the ram pressure, you get a completely different state where the pressure is so large that it can push back against the accretion flow, and you see it being sort of pushed back periodically. And so you have these periodic, very strong periodic variations. So these two classes of accretion flows are called, in the literature, I think Ramesh had a lot to do with these names, SANE and MAD. So SANE stands for standard and normal evolution. MAD stands for magnetically arrested disk. And I hope at least one person gets that reference, but if not, that's okay. It's not important. So SANE versus MAD. So to go into more detail, so now I'm going to show some figures from Igumenishev 2003, which was the first set of simulations that really studied the magnetically arrested disk after simultaneously with Ramesh describing it theoretically in his 2003 paper. So on the left is going to be SANE, on the right is going to be MAD. So the left is a poloidal slice through the flow. So this wraps around like this, if you can see me. And and on the right is a phi. So this is also, the one on the left is fairly axisymmetric, so it's not shown in it's a toroidal slice is not shown. On the right is a toroidal slice through a MAD simulation, and you see there's these accretion streams that sort of flow in as opposed to this thick disk. And also, if you look at the magnetic field lines, so these are magnetic field lines. On the left, if you look within the torus, it's very turbulent. You have all these loops and tangleness. On the right, it's coherent and largely vertical. So that's the magnetically arrested case. So I'm just going to break down the differences between SANE and MAD, just some basic differences. So first, the SANE generally has a toroidal field, which is wrapping around with this rotation of the disk, because it's relatively weak and gets dragged with flow. The MAD is mostly poloidal, or at least it has a large poloidal component because it can resist this motion. Then the SANE is driven by the MRI. The MAD actually has the MRI is suppressed because of the strong field. SANE has stronger turbulence. And the SANE also has stronger axisymmetry, where the MAD is highly non-axisymmetric, as I just showed. SANE is roughly Keplerian rotation, so rotation supported, while the MAD is sub-Keplerian, so less rotationally supported. MADs have stronger jets because they have stronger fields, which provides stronger pointing fluxes. SANE is thicker, MAD is thinner, because the magnetic field sort of compresses the flow. And then the variability in the same case is due to turbulence, sort of stochastic and random, or MAD. The variability is more extreme, but it's also more periodic. You have these where the ejection events, where the flow gets pushed outwards, happen on a sort of almost periodic timescale. So, okay, so there's these very strong differences between these two types of flows. And what determines what state you end up with in your simulation is based entirely on these initial conditions. So what the problem really is when you're saying that we can't distinguish between mad and sane just by certain observations alone, the problem is that we have too much freedom. And the American and the brave heart in each of us might object to such a statement, but if anybody has been watching Netflix recently, you realize when you have too much freedom, you can end up with a bunch of tigers in your backyard, which might not be recommended. So anyway, we want to take away this freedom. So you can think of, that's what I set out to do. So you can think of me like the TSA of GRMHD simulations, taking away some of the freedom in order to have a more successful or a more enjoyable or a more safe experience. So how do we do this? Well, we can go back to what I was describing before. We have these observations of the gas at larger scales. And in fact, we have even better observations than I described, because each of the stars, each of the Wolf-Rayet stars, we know mostly its mass loss rate, its wind speed, its orbits. So all the hydrodynamic properties of these winds, we know we are pretty well constrained by observation. So if we could, in principle, incorporate these into simulations or analytic calculations, we could have more a priori knowledge about the accretion flow. And this has been done in the past. So first there was these 1D models. So Elliott Quadert just had a basic model of, you have the hydrodynamic fluid equations, then you add some source terms that describe the feeding of mass via these stellar winds, sort of into one smooth source term in mass, angular momentum, and energy. And this produces a flow which can match, this is the X-ray surface brightness, I think, or no, this is the density, which can be mapped to the X-ray surface brightness at the two different scales that was observed by Chandra in 2003, and you can roughly match these X-ray observations. Then again, you can do something more sophisticated. So this is Roman Sherbakov in 2010. He used more physics. They used more physics and also a more sophisticated source term that actually took into account each of the individual mass loss rates of the wind. So it's not just smooth. You see the bumps and spikes. That's what this is showing, just a source term basically. And then they also compared to the X-ray data now on many more different scales. So that's what all these data points are instead of just the two. And they were able to fit it very well using sort of an inflow-outflow model that incorporated the stellar wind mass feeding rate. So all this to say that the amount of matter provided, this is just including the Wolf-Rayet stars. So all this to say is that the Wolf-Rayet stars provide enough mass to reasonably explain the hot gas at large radii. Then one Avi Loeb realized in 2004 that, you know what, there's all these stars, but if you just look at one star that has plenty of gas, or that has plenty of mass, the mass loss rate is large enough to provide the bulk of the accretion just by itself. So you can do sort of this little model where you have an orbiting eccentric star, or even on a circular orbit, where some of the gas gets accreted, some of the gas doesn't. And what determines whether it's accreted or not is just the angular momentum. So if the wind speed of the orbiting star is roughly equal to the orbiting speed of the star, then you can imagine that, so in the frame of the star, if you just sit with the star, the wind is spherical. But if you jump into the frame of the black hole, the stuff that's emitted in front of the star in terms of its orbit will have too much angular momentum to accrete. The stuff emitted behind it will have lower angular momentum, and only a fraction of that will actually have low enough angular momentum to reach the center. And so that's sort of what the little diagram on the left is showing. Red is unbound, blue is bound, and each of those lines is sort of a parcel of gas being emitted by the wind. And so only a small fraction of this reaches the black hole, and that could explain the small accretion rate just based on like the stellar wind dynamics and the addition of velocities. And what generally tends to happen is that the closest star, and in this model, the closest star provides most of the accretion, but then over time, as the orbit shifts, another star becomes closer. So then that provides the bulk of the accretion, and you can actually, so over time, multiple stars do contribute to the accretion budget, but at a single instance, it's mostly dominated by one star. So that's the idea. And so keep this model in mind as we go forward. Okay, finally, then you can go to 3D simulations. So this has been done in a series of works by led by Jorge Quadra. And you incorporate all the data into these 3D orbits You put them into a simulation. That's what this is showing. Density on the left, temperature on the right. And these move through the domain, feed the gas in, and you can now study the gas in more three-dimensional detail. And again, so this is now the accretion rate as a function of radius on the top. On the bottom is sort of the closest stars that are, as a function of time, the radius of each individual star. So all these 29N, those are the Wolf-Rayet stars, 16C. So what the top is showing is the accretion rate broken down into individual components of each of the stars. So it does, so that what this shows is that only 2 or 3 of the stars contribute to a bulk of the accretion. And so this is sort of confirming the idea that Avi had, that it's just might be just one star most of the time contributing to the accretion. But what you also notice is that the accretion rate is relatively high. So this is 2 to 4 times 10 to the minus 6 solar masses per year. And that's much higher than what's actually reaching the black hole. So that's a problem. So something's wrong with this model, and what is it? So there are 2 possible issues. One is that the inner boundary for the simulation is incredibly large compared to the event horizon. So 9,000 M versus 2M for a non-rotating black hole. And there's also no magnetic fields, which have, of course, can have a very important effects on the dynamics. So I want to rectify both of those, or I want to at least explore those 2 possibilities. So that's where I'm going to start with what I added to all this. So first, you can just add magnetic fields to the simulation. So the problem is that we don't have particular observations of the magnetic fields of these particular Wolf-Rayet stars. However, we can use theoretical considerations to see that the field is probably going to be in the phi direction, or in just wrapped around the star, because these parsec scales are much larger than the radius of these stars. And just by flux conservation of magnetic field coming off of a wind, by the time you get to these large scales, the radial field will be very small. The phi field will be dominant. Then we have observations of O stars that show that about 5 to 10% of them have fairly large magnetic fields. So it's reasonable to expect that these magnetic fields will be present in these stars, at least some of them. So what we do is we parameterize each of the winds in the model with some parameter that's the ram pressure divided by the magnetic pressure, which I call beta wind. And so this is a constant just because rho is 1 over r squared, the wind speed is constant. The field, as I just showed, scales as 1 over r. And then for each of the stars, you have to determine what is the phi direction, which is determined essentially by the spin, which we don't know. So I just choose random directions for each one. And so what I'll show from now on will be 2 particular choices for beta wind, 10 to the 2 and 10 to the 6, and 1 particular realization of the spin axis. So hopefully, our hope is that it doesn't depend much on these parameters. And particularly the spin axes, we've done a bunch of random spin axes and showed that it is not sensitive to this. How much time do I have left? I can't see a clock on here.
Yeah, just go, no worries.
Okay.
Yeah.
I didn't know if you just showed up because it showed me that I had like 5 minutes left or something. Okay, 3D. So this is now, I'm going to show you the simulations that I did. So these are now on basically the same scale as Jorge Quadra simulations, except the inner boundary radius is much further in. It's something like 300 M. It's still not all the way to the black hole, but it's further in. And now they have these magnetic fields. So the bottom right is a snapshot, which shows the magnetic fields in white and the density in this. So white density is high, green is low. And then on the left will be a slice, just a movie of these stars orbiting around. And you just see how they move through the domain. They add a bunch of mass. They interact with each other. So this is a 10,000 year movie. And it's about a parsec in scale, the 1 parsec by 1 parsec, roughly. And then you see also there's some cool clumps that form, all this kind of cool stuff. And there's stuff building up in the center. And then you can zoom in on this.
Sean, can I ask a quick question?
Yeah.
So these Wolf-Rayet stars are orbiting the galactic center, but they're much farther out than the F stars, right? Or are they at the same radius? Yeah,
they're about a factor of 10 further out. But the issue with the S stars is that they have maybe about 3 orders of magnitude less accretion rate or less mass loss rate than the Wolf-Rayet stars. So I
Okay.
have put in some S stars, and it doesn't affect anything. If you put in like the mass loss rate of like 10 to the minus 8 or something solar masses per year.
I see, but I guess what I'm getting at is it's clear that the Wolf-Rayet stars are bound to the black hole.
Yes, some of them at least. I think some
Okay.
are on such long orbits that you can't necessarily tell. There's like one, maybe.
Okay, I just wanted to make, because in the simulation they're sticking around for many, many orbits.
Yes, but generally the important stuff happens on the time scale of like 1,000 years. So it's not over, most of the stuff is not over many, many orbits, except for maybe 1 or 2 of the stars.
Okay, all right, thank you.
You're welcome. Okay, so this is now about 10 times further in, just to show you zoomed in. You see how these stars just get they get close, they add some mass, and sort of rotating around. You'll see that they're rotating in sort of a clockwise, that a lot of them are, I think they're counterclockwise because the movies flip backwards, but a lot of them are in this counterclockwise motion. So in reality, this represents the clockwise stellar disk, which contains about 1/2 of the stars. And so this should be clockwise. It's just reversed because of the way I plotted it. But a lot of these stars, especially the innermost ones, are in a well-defined disk. So that's important to remember. Okay, so I have these simulations now. So I'm not done, but I would like to just see if what I'm doing is reasonable. Again, comparing to some of the observations, to see if we're not doing anything crazy. So you can look at the X-rays. So a spatially 2D map of the surface brightness. The left is what's observed, and the right is the simulated at the same resolution. It's not, obviously it's not a perfect match, but it's not completely crazy. You see it's reasonable in terms of the magnitude, and some of the spatial distribution is similar, but we're not trying to fit this like perfectly just to get something reasonable. So ignore the bottom left for a second. The bottom right is the same thing essentially, but as a function of time and at 2 different scales. So measuring the X-ray luminosity at a larger scale and a smaller scale. So the smaller scale is like right around I can't see my mouse, but right around the center of the images. And what you see is that's the top in the plot on the bottom right. So that tends to be a little too high, which you can see just by eye in the 2D contour. But then the larger scale on the bottom can be reasonably explained by the simulation. So it fits pretty well at larger scale, which is also, you can sort of see that by eye. So if you just excise the middle, just put a little circle in the middle and remove that, they would look roughly the same magnitude if you integrate over the whole domain. That's what that's showing. So again, it's not perfect, but it's not crazy. It's not off by a factor of 10. It's off by maybe a factor of 2 in terms of the X-ray luminosity at small scale. So it's not crazy. Then the bottom left is, I won't go into the details of this, but it's the rotation measure as a function of time, which is a measure, essentially the integral of the density times the magnetic field pointing at us. And if you compare this to the observations we have of the rotation measure in 2006 and 2018, you can get reasonable magnitudes and time variability from the simulation. So there's a lot of detail that goes into that, so I won't go into more. You can ask me about it later. But it's reasonable, again. And again, sorry for the graininess of this plot. It's not because of the graininess of the simulation. It's because of I put it onto when I plotted this, I put it onto a smaller grid, a lesser fine grid, so it shows up kind of clunky. But this is just to show, again, zooming into smaller scales, that you see there's this one star providing a lot of material that spirals inwards. And so one or 2 stars, there's another one right on the bottom left, provide a bulk of the accretion rate. And then that turns into, that star then determines the angular momentum of the accretion flow at small scales. So this is the angular momentum vector broken into X, Y, and Z components as a function of time compared to, so the dotted dashed lines are the stellar disk and the lines are the simulation. So mostly just focus on the yellow line, which is where most of the angular momentum is pointed. So it's mostly in this clockwise disk. And it's sort of, as a function of time, it reasonably matches the angular momentum of the stellar disk. So that is provided by the fact that all this gas is provided by mostly one star. That's why you have such a coherent angular momentum direction. Okay, but this was still all very far away from the black hole. At most, or at smallest, it was 300 M, and there it wasn't particularly well refined. So what I want to do now is go to smaller scales, but it's not inherently obvious how to do this, because a single simulation will never be able to do this, at least not on modern computers, because the domain is like 7 orders of magnitude in radius, and the time scales are so disparate that it would cost a ridiculous amount of computational time in real time. So I kind of cheat, or I'm clever, depending on how you define it. I use multiple simulations. So I get this data from the first simulation, I run it to the present day, then I take a portion of that data. So what this is just the radius. This is just a schematic. Radius on the x-axis, the y-axis is meaningless, it's just a diagram. And I take a portion of the data from the large scale simulation, I import it into a smaller scale MHD simulation. I run that for long enough to reach a steady state based on the fixed initial conditions from the original simulation. I run that for a certain amount of time, then I take that data and do the same thing, and then I finally import it into a GRMHD simulation. And the hope is that this will then produce basically wind-fed initial conditions for GRMHD that are not based on like a torus model, but just based on this physics of the stellar winds. And the dashed lines here that you see in the yellow and the purple are where the simulation is not particularly well resolved. So that's why I don't import that data. I just sort of throw it away. And so I have these 3 simulations. I just run the first, run the second, and then I start the third, the GRMHD simulation, which is what I'll now focus on, the GRMHD simulation. So this is a scale of about 50 RG in radius, or 25 Schwarzschild radii. And you see the part that I excised from the initial conditions. That's the green is essentially the floor, where I took away the part that was unresolved from the MHD simulation. And the simulation extends to much larger radii. This is just where I'm focusing on, so it doesn't cut off right at this edge. And I'm just going to show what it starts. It starts off just adjusting to the initial conditions, and then you get this accretion flow. And I'll just let it go for a second. And you'll notice a couple things. Oh, so I should mention that the frame that I'm plotting this in, the angular momentum direction of the initial conditions, if you average over the initial conditions, the angular momentum director is up. And so it's tilted with respect to that direction, you can see. And eventually you start to see magnetically arrested behavior. You'll see it start pushing out some of the gas, especially on the left side. And I'll just let it keep going for a second. Yeah, so it's particularly thin on the left side, and there's lots of, yeah, there you go. So it pushes it out, and this behavior sort of continues. And I'll just, okay, I can cut it now. Okay, and so that's a movie of what's happening, but but is that actually reasonable based on what I put in as the initial conditions? Like, is it consistent? So in fact it is. It's at least self-consistent, in the sense that if you plot the various quantities in each of the 3 simulations, they overlap across the domain. So you have a consistent solution for the density, the magnetic field, the temperature, and all the other quantities. So these are just various fluid quantities function radius, so they tend to be power laws, and they nicely overlap, at least for the most part. Also, the simulations are fairly observationally consistent in terms of the density profile as a function of radius. So there's this estimate from Stefan Galesin and collaborators based on 7 different observational probes of the density at 7 different scales using 7 different methods. So that is this dashed white line, as well as the yellow. The yellow is sort of an older estimate, and the yellow line, while the dashed white line is the updated estimate. And the simulation data is the blue solid lines plotted on top of each other. And you see that they're right in between these two estimates. So they're doing something reasonable, right order of magnitude, right rough power law, r to the -1. So that's encouraging because this didn't necessarily have to work out like this. So that encourages us that we can now study the GRMHD simulation in more depth and think that we're getting something meaningful. And as I mentioned in the movie, it does clearly seem to be magnetically arrested. And so this quantity phi BH is the magnetic flux threading the horizon. In other words, it's that quantity that I mentioned before, where 50 is the saturation value. And you see it saturates at roughly 50. And these cycles where it builds up and then rapidly decreases, those are very typical of magnetically arrested disks. They're dissipation events, the flux dissipates, that's where you see the ejection of matter. So the flux decreases after everything's ejected and then it builds back up, then ejects again. And on the bottom is the accretion. So, I should mention that the solid line is the 1 beta 10 to the 2, while the dashed line is beta wind of 10 to the 6. So these are the parameters defining the magnetization of the stars. And you can tell that it's roughly independent of beta wind, which is very encouraging because those were 2 parameters that we essentially just chose out of our hat. And so the accretion rate, in terms of the accretion rate, it tends to be about 10 to the -8 solar masses per year, which is a very reasonable number given previous estimates. So if you recall, the larger scale simulations had accretion rates of 10 to the -6 or so, which was much too large. But now that you go all the way down to the black hole, not all of it reaches the horizon. So that's encouraging as well. So lots of things seem to be encouraging. Again, not strongly dependent on beta wind. That's important because this is one of the free parameters that we have in the model. And so it seems to be that a magnetically arrested disk is what we predict to form based on the wind accretion model. And this is corroborating several other results that have happened just in the past couple years that point to the galactic center being a magnetically arrested disk. So first of all, well, not first of all, but one recent paper, Jason Dexter studied the fraction of light that's polarized that comes from the smallest scale, so the linear polarization fraction. And he broke it up into several different models that are SANE and MAD. And so the observed polarization seems to rule out most of the SANE models because they tend to be depolarized. They have lower temperatures, higher densities, which leads to larger Faraday rotation, which tends to, they spatially depolarize the image. And MAD models tend to do this less and are thus tend to be favored. So this is some argument why a MAD model might be more appropriate. Then we observed by the gravity interferometer, observed these orbiting flares. So you see in the infrared, you see these flares that, at least during this time period, they saw flares that showed up and they orbited the black hole about once and then disappeared. And they had a particular polarization pattern. This is a very subtle argument, so I won't get into it. But the polarization pattern of the flares so this is U versus Q in Stokes parameters. In other words, the polarization vector of the light that we observe is rotating, and it rotates in sort of a loop like this. So this is one orbit. And this loop structure tends to require strong or poloidal fields, significant poloidal fields, which points to a magnetically arrested disk because the field must be strong enough to resist the flow of gas, which in a SANE model tends to get wrapped up in the phi direction. Finally, just the flare orbiting, just the flare orbiting itself, which happens at about 10 gravitational radii. The fact that it's happening at such a radius is pointing to a MAD model as well, because these flux ejection events create these hot spots that move around and orbit the black hole. And this is behavior not really seen in SANE simulations, but it is at least approximately seen in MAD simulations. So there's some reason there's lots of reasons to, particularly recently, to think that the galactic center is MAD, and that's consistent with what we're finding. And then I don't have much more, but just to elaborate on the tilt. So if you remember, the disk that I showed was sort of tilted. and that tilt oscillates in time by about 10 to 20 degrees. So what causes this? Oh, I should have mentioned the black hole is not rotating in these simulations. That's very important. A is 0. A is the dimensionless spin of the black hole. So what is causing this tilt then if it's not the spin? So initially the angular momentum is pointing up, so you would expect the disk to be in that plane. However, the magnetic field initially is slightly tilted compared to the angular momentum, and this is not something that we did on purpose. This is not something that we control. This is just determined by the physics at large radii. So the initial magnetic field is slightly tilted, which then causes the magnetic field is so strong that it tilts the disk in this way, and you get this configuration. So that's just saying the magnetic field direction determines the disk inclination. And then now this is just the 230 gigahertz. This is sort of preliminary. So not to go into detail, but you need to prescribe electron temperatures in these models because they are collisionless and electron and proton temperatures are not in equilibrium. So you have to paint on electron temperatures, at least in this preliminary stage. So we choose particular parameters that set the flux at a reasonable level, 2.4 Jansky at 230 gigahertz, for instance, and we get something like this. So this is going to be the intensity, and the green lines are polarization vectors. And you'll notice that this is a edge-on inclination, which is, again, that's not something that we fixed. This was determined by essentially the magnetic field direction, which determines the orientation of the disk. And this is for the 10 to the 2 beta wind simulation. And you just see the variability as a function of time. This is probably longer than it needs to be, this movie. But I'll show you, I'll skip ahead at a certain point to see some of the variation. It's pretty cool. And then I also have it at the end, it gets blurred to the EHT resolution. So I'll skip ahead to the blur. So now this is the blurred version where you just see, so it's much more fuzzy and the variability is fairly interesting. The right is lighting up because that's the part that's coming at us in terms of the rotation. Left is going away from us. And this is about a 10 or a 20 Schwarzschild radii across in, I think that's actually should be RG. I think it's 20 RG by 20 RG. And this whole movie lasts about 2 days. So that to give you an idea of the variability. And so if you measure the polarization fraction from this image, which is the number that I quoted before that was tend to be ruled that was too small for the SANE simulations, it's in very good agreement with observation 6.8 compared to the something that I can't see because my thing's over it, but it's in reasonable agreement with it. I think it's like, I can't see it. Yeah, 3.6 to 7.8. And so it's right in that range. So that's good. And then finally, the 10 to the 6 simulation. So the interesting thing here is that now the beta wind of 10 to the 6, which has most of the same dynamics in terms of the fluid quantities averaged over radius, the magnetic flux, but what does seem to be different in the simulation is the orientation of the disk at small scale, which is now edge on. So now we're basically looking down the disk is perpendicular. It's rotating in the plane of the sky. So it's much more, you see the ring of emission much more clearly. It's much more axisymmetric. And again, this just has to do with the direction of the magnetic field coming in from large radii, which sets this. It just so happens that the beta wind of 10 to the 6 is mostly face on and the beta wind of 10 to the 2 is mostly edge on. This is not robust to beta wind of 10 to the 2 or beta wind of 10 to the 6, unfortunately, because that would be an easy way to predict things. And again, this is just blurred. You see the variation. And I believe, so the important thing about these, one of the cool things about these movies and these images is that we don't have the freedom to change the accretion rate. So that was determined by all the physics of stuff coming in. All we have choose from is the electron temperature. So it's encouraging that the electron temperature model is something reasonable. It's not something crazy that we have to put in order to match the emission. And I believe that is it. So just still to come, of course, we have to look at what happens when you put in a rapidly rotating black hole, because that could very much change things. There would be relativistic jets. It could tilt the flow. There'd be feedback, all this kind of thing. But of course, there's also the possibility that it's not spinning at all, which is suggested by some of the orbits of the S stars, by the fact that there's these potentially two disks, and that the disks have remained stable over time. And then also we would like to eliminate this electron temperature parameter that we have just sort of put in by hand by doing 2-temperature GRMHD, where then we would have even less freedom to choose the physics that goes in. And then we would look at spectra, rotation measures, emission variability, all this kind of thing, which we haven't really looked at yet because we want to have this electron temperature self-consistency in there. And that is the end. So thank you.
Thank you, Sean. This was a very interesting flyby on Sagittarius A star. So questions, Avi?
Sean, thank you for an excellent talk. The question I have is that many of these stars that we see, the S stars and also the more distant stars, they often lie in preferred orbital planes, which indicates, just like the solar system, that the planets originated from a disk of gas to start with, and the same must be true for those young stars. They came from a disk of gas. So it's sort of like a chicken and an egg. I mean, so, okay, now the stars are prominent in terms of contributing mass to Sag A star, but before they existed, there was a disk of gas. Presumably, Sag A star was fed from this disk of gas. Can you speak a little bit about, I mean, obviously we are seeing it very starved right now, so the stars can participate in the process of feeding it, but there used to be gas that fed it probably much more.
Yes. So the simulations that I'm doing, of course, they don't go back that far. So, but I think what would be interesting, that's a strong argument for the spin of the black hole, if it has spin, to be aligned with the rotation of the actual angular of the disk coming in. Because if that's being fed from the same disk, then it was spun up by the stuff pointing in the same direction.
So that can give us a constraint. The spin of the black hole can give us a constraint as to how much mass accreted, onto it in the last episode.
Yes. Right. Yeah. So I guess you could get some. Yeah.
Mm-hmm.
Shep. We can't hear you, Shep.
He's muted. Can someone unmute him?
I could unmute him, but
well, hold on. Can you guys hear me now?
Yes.
Yeah.
Okay, I was on some kind of Bluetooth thing that malfunctioned. So these have been spin zero simulations, right?
Yes.
Yeah. So from the simulations you've done, wouldn't you be able to see time variability that would be related to the spin of the black hole? Because you showed us some simulations close in that you can clearly see rotation around the black hole, at least in the last one that you showed. I think it was the 10 to the 6 one.
This one?
Yeah, and it seemed to me that you could see rotation around there, and the orbital period, it must be related to the spin somehow. Is that not true?
Oh, well, so the rotation here is provided just by the angular momentum of the gas coming in. The black hole itself is not rotating. But that does set an orbital period, which tends to determine the time scale of like the turbulent variability.
I guess I was asking if you had non-zero spin, would that affect the orbital periods of the bulk motion you're seeing?
I believe it would, but it's not clear. It really depends on whether the spin is aligned or not with the flow. Like Avi, we were just arguing that potentially it is completely aligned, which would have probably the smallest effect. But if it was completely anti-aligned, going in the exact opposite direction, it could have a dramatic effect. It would push the ISCO out to much larger radii, and the period would then that you observe at that radii would then go down. or up, the period would go up, the rotation rate would go down. And I think spin is probably the most important thing that we did not include, because I think it could dramatically, it's all this tilt and that could very much just be completely altered by if the spin is not aligned.
Yeah, I mean, the other argument for no spin historically has been that there's no jet that we can see from this source. And my understanding of the gravity results is that the face-on kind of configuration is preferred. And I guess the jet can still be alive if it's pointing directly at us, which seems a little bit contrived, but I guess it could still happen.
But lots of things in the Galactic Center seem to be sort of contrived, so it wouldn't surprise me too much.
Yeah, it is a unique environment, as they say. Thanks a lot.
Yeah, the other possibility is that there's a jet, but we're not really seeing it, because so I have a lot of, in a simulation, it only becomes disky like this, where you have the mid-plane sort of evacuated of matter, or not the mid-plane, the polar regions evacuated of matter only happens at small radii. So at large radii, there's sort of more spherical distribution. And the jet, if it's not strong enough, might not be able to penetrate that material, and it would just sort of disrupt before it gets to large radii, and that could also lead to us not seeing it. So there's a couple things that could be happening. And I see.
So there would be any jet on larger scales.
Yeah. And you do see sort of these bipolar outflow features at much larger scales. So people have argued that is evidence of a jet, but it's very not clear and not well explained at the moment.
All right, thank you.
We have Ramesh.
Yeah, so Sean, this is terrific stuff. It's really interesting. So you're finding that at least your simulation has become kind of pretty much mad near the black hole. So I'm just wondering, how far out does this mad zone extend? Is there any range of radius where you actually see a regular MRI?
No. So even in the larger scales, I never saw MRI, perhaps for a different reason. In the larger scale simulations, and going out to larger scale in the GRMHD simulation even, it's not very rotationally supported. You have very large radial velocities. So it never really has time for the MRI to build up. It's sort of inflowing and outflowing at a rate much faster than the orbital time scale. But beta is also fairly low out to large radii, like 10 to the 4 gravitational radii.
Yeah, it is that signature that I would interpret as saying that this is kind of, if not fully mad, semi-mad throughout the flow. It never really becomes a proper disk with MRI.
Right.
That's really interesting.
Yeah, so it's sort of weird even calling it a magnetically arrested disk. It's more like just a magnetically arrested flow, but that doesn't sound as cool.
Yeah.
All right, Richard.
Yeah, so I'm just wondering whether gravity has enough, I guess, duration of observing these polarized loops in the UV planes to make such strong conclusions as to whether the disk is sane or mad. If the loop polarization it may make one loop in one cycle, but then what's to say that if you observe it for a few more cycles, or if you observe new ones, if they're just coming in and out and disappearing, have we observed them nearly long enough to conclude that the disk is in one accretion mode and it's persistent or robust? And another is that could there be just enough poloidal flux to account for the hotspot polarization spots to make one loop, but not enough poloidal flux to make the disk completely mad?
So the first question, for each individual flare seems to only last about one loop before it disappears. And then we only have, at least published, I think we only have 3 I say we, but they have only 3 published flares. And this one that is shown is the best looking one. So the other ones are not as obviously rotating in this manner. So I agree that it's not necessarily, like, you would definitely want a larger number of flares before you make definitive conclusions. But I'm not sure what exactly, I think they have more data, but there's something, I heard there was some issues just with the data interpretation in the more recent things or something like that. I just heard rumors. But so there haven't been any further release of flares. So, but I guess so all of that analysis is mostly for like this one, I call it the Cinderella, or is it the Goldilocks? No, what did I call it? I don't know. I call it something that I can't remember, but it's the one flare that is the most presentable, that's done most of this analysis on. So it's definitely possible that this is sort of a one and done kind of thing, and it even might not even be in the bulk of the disk. It could be like in a spiral outflow or something. So there's a lot of debate over that. But also, the second question was that could it just be a significant amount of colloidal flux in a semi or something like very close to MAD, but not necessarily MAD? I think that's definitely a possibility. MAD, I think it requires, like, if I think Jason looked at both MAD and SANE, and he tend to, even MAD, to had like just barely enough colloidal flux to do this, but I could be wrong. I could be misquoting him.
Yeah, so I definitely agree that it's far from settled science whether the galactic center disk is MAD flow and whether it's face on. And I would definitely like to see more flares, especially the ones that they're more reluctant to show.
Agreed.
All right, last question from Angelo.
Hi, I wanted to ask you about your rotation measures. It was interesting that you're in the right ballpark and that there was variability, but it was stable enough to maintain the same sign for a few decades, if I remember your plot correctly.
Yes.
And so I wanted to know, at what radius is this RM being accumulated, and does it have anything to do with the accretion rate? Or maybe for the larger box, your inflow rate into the inner boundary?
Hopefully it's not on one of these slides with the, here it is. Yeah, so those are very good questions. And so the bulk of it appears, the bulk of the rotation measure is dominated by a few hundred Rg, where the electron temperature, at least, so this rotation measure was calculated assuming the electron temperature is equal to the gas temperature, which is probably not a great assumption, but we have not, that's why I want to add actual electron physics in here so that I can get a more reasonable calculation. But so 300 Rg is where it mostly happens. And that's where the electrons become relativistic. So below that range, they become more relativistic. So most of the, and when they become relativistic, of course, the rotation measure is suppressed.
Mm-hmm.
So it is a fairly good tracer of the accretion rate just because of this. So it's basically point source emission at that point. So you don't have to worry about all the depolarization effects. So that's a good thing in that sense. And what was the rest of the question? I forget, sorry.
That was it, yeah.
Okay.
Thanks.
All right, so lots of questions today. Let's talk our speaker again, and see you next week. Thank you everybody for being with us.
Yeah, thank you for having me.
Yeah.